Yes, an open neutral can indeed cause higher than phase-to-phase voltages. In a typical electrical system, the neutral wire serves as the return path for current, completing the circuit back to the source. It's usually grounded at the service entrance, maintaining a voltage potential close to zero. However, when the neutral wire is open, this return path is disrupted. The current that would normally flow through the neutral now seeks alternative paths, often through connected equipment. This can lead to an imbalance in the voltage distribution across different parts of the circuit. In a balanced system, the voltage between each phase and neutral should be approximately equal. For example, in a 120/240 volt system, you'd expect around 120 volts from each phase to neutral. But with an open neutral, this balance is disturbed. Loads connected to one phase might experience an elevated voltage, while those on the other phase see a reduced voltage. This voltage imbalance can be significant, potentially exceeding the rated voltage of connected devices, leading to overheating, damage, or even failure. In the case of the outlet strip with the surge suppressor, the open neutral could have caused the voltage on one of the phase wires to rise considerably, possibly reaching 208 volts, even if the system was designed for a lower voltage. This overvoltage stress on the surge suppressor's varistors, which are designed to clamp voltage spikes, could have led to their overheating and eventual failure, manifesting as burning or flame. To understand this better, consider a simplified scenario. Imagine two resistive loads connected in series between two phases, with a neutral point between them ideally providing a balanced voltage. If the neutral connection is broken, the loads are now in series directly across the phase-to-phase voltage. The voltage across each load will depend on its resistance. If the loads have significantly different resistances, the voltage will divide unevenly, with the higher resistance load experiencing a higher voltage. This is why an open neutral can cause some devices to receive a dangerously high voltage while others might receive a lower voltage. Now, to simulate this condition in a lab setting, you can use a variable transformer, often referred to as a variac, to gradually increase the voltage applied to the line wires. You'd start with the normal operating voltage, say 120 volts or 240 volts, and then slowly increase it while monitoring the voltage across the terminals of the outlet strip. If the neutral is indeed open or disconnected in your test setup, you should observe the voltage across the terminals rising above the expected value as you increase the input voltage from the variable transformer. The key here is to ensure that the neutral wire to the outlet strip is intentionally disconnected to mimic the open neutral condition. This allows you to observe the voltage imbalance and the potential for overvoltage on the line wires. Measuring the voltage across the terminals of the outlet strip under this simulated open neutral condition should demonstrate the increased voltage, confirming the effect of the open neutral. This overvoltage can stress components like varistors and surge suppressors, potentially leading to overheating and failure. Here's a more detailed breakdown of what happens when a neutral wire becomes open. Firstly, in a standard electrical system, the neutral wire is connected to the ground wire at the service entrance. This connection ensures that the neutral wire and the ground wire are at nearly the same voltage potential, providing a stable reference point for the electrical system. Secondly, when a neutral wire is open, the current that would normally flow through the neutral wire is forced to find alternative paths back to the source. This can lead to current flowing through the equipment connected to the circuit, creating voltage imbalances and potential hazards. Thirdly, the voltage on the line wires is also affected by an open neutral. Normally, the voltage on the line wires is equal to the voltage on the neutral wire plus the voltage drop across the load. However, when the neutral wire is open, the voltage drop across the load increases, causing the voltage on the line wires to rise as well. This increase in voltage can exceed the rated voltage of the connected equipment, leading to damage or failure. In the specific scenario you described, the voltage on the line wires increased to 208 volts because the neutral wire was open. This overvoltage condition caused the surge suppressor to overheat and fail. In summary, an open neutral can lead to voltage imbalances and overvoltage conditions that can damage or destroy sensitive electronic equipment like surge suppressors. Understanding how an open neutral affects voltage distribution is crucial for troubleshooting electrical problems and ensuring electrical safety. When dealing with electrical issues, always exercise caution and consult with a qualified electrician to avoid potential hazards. The open neutral can also lead to an increase in harmonic currents circulating within the system. Harmonics are multiples of the fundamental frequency, typically 60 Hz, and can cause various problems, including overheating of transformers, conductors, and equipment, as well as interference with electronic devices. An open neutral can exacerbate harmonic distortion as it disrupts the normal flow of current and creates nonlinear loads. This can lead to a buildup of harmonic currents, which can further contribute to voltage imbalances and equipment failure. In addition to the immediate effects of overvoltage, an open neutral can also have long-term consequences on the electrical system. Repeated exposure to voltage imbalances and harmonic distortion can degrade insulation, reduce the lifespan of equipment, and increase the risk of electrical fires. Therefore, it is essential to address open neutral issues promptly to prevent further damage and ensure the safety and reliability of the electrical system. When troubleshooting an open neutral, it is crucial to use appropriate testing equipment and follow safe electrical practices. A qualified electrician can use a voltmeter to measure the voltage between the neutral wire and ground at various points in the circuit to identify the location of the open neutral. It is also essential to inspect the wiring and connections for any signs of damage or corrosion which can contribute to open neutral conditions. Additionally, it is important to verify the integrity of the grounding system to ensure that it is providing a reliable path for fault currents. A properly grounded system can help mitigate the effects of an open neutral by providing an alternative path for current flow, reducing the risk of overvoltage and equipment damage. In conclusion, an open neutral is a serious electrical problem that can have significant consequences for the safety and reliability of an electrical system. Understanding the causes and effects of open neutrals is essential for troubleshooting electrical issues and preventing equipment damage. Always consult with a qualified electrician when dealing with electrical problems to ensure that the work is performed safely and correctly. In addition to the practical aspects, it's worth noting some theoretical considerations related to open neutrals. In a purely resistive circuit with a balanced load, the neutral current should ideally be zero. However, in real-world scenarios, loads are rarely perfectly balanced, and there are often nonlinear loads that draw current in a non-sinusoidal manner, resulting in harmonic currents. These factors contribute to a non-zero neutral current even in a healthy system. When the neutral is open, the current that would normally flow through the neutral is forced to redistribute through the phase conductors and ground, leading to complex current paths and voltage drops. This redistribution of current can create circulating currents and further exacerbate voltage imbalances. Moreover, the impedance of the various circuit elements, including conductors, connections, and loads, plays a crucial role in determining the voltage distribution in an open neutral situation. Even small differences in impedance can significantly affect the voltage across different loads. Therefore, a thorough understanding of circuit theory and impedance concepts is essential for analyzing and troubleshooting open neutral problems effectively. Furthermore, the National Electrical Code (NEC) provides specific requirements for grounding and bonding to minimize the risks associated with open neutrals. Proper grounding and bonding ensure that there is a low impedance path for fault currents, which helps to protect equipment and personnel from electrical shock hazards. The NEC also mandates the use of ground fault circuit interrupters (GFCIs) in certain locations to provide additional protection against electrical shock. GFCIs are designed to detect even small imbalances in current between the hot and neutral conductors, and they quickly trip the circuit to prevent electrical shock. In summary, an open neutral is a complex electrical problem that requires a thorough understanding of circuit theory, grounding and bonding principles, and the NEC requirements. By following safe electrical practices and consulting with a qualified electrician, you can effectively troubleshoot and resolve open neutral issues, ensuring the safety and reliability of your electrical system. Let's further explore the potential causes and preventive measures associated with open neutrals. Open neutrals can arise from a variety of factors, including loose connections, corroded wiring, damaged conductors, and faulty equipment. Loose connections are a common cause of open neutrals, especially in older electrical systems where connections may have deteriorated over time. Vibration, thermal cycling, and improper installation can all contribute to loose connections. Corroded wiring can also lead to open neutrals, as corrosion can weaken the conductors and create high resistance connections that eventually fail. Moisture, chemicals, and pollutants can accelerate corrosion. Damaged conductors, such as those that have been nicked, cut, or crushed, can also cause open neutrals. Physical damage can compromise the integrity of the conductor and lead to breakage or insulation failure. Faulty equipment, such as circuit breakers, receptacles, and switches, can also contribute to open neutrals. Defective components can create high resistance connections or interrupt the neutral path altogether. To prevent open neutrals, it is essential to implement a comprehensive maintenance program that includes regular inspections, testing, and repairs. Inspections should focus on identifying loose connections, corroded wiring, and damaged conductors. Connections should be tightened, corroded wiring should be cleaned or replaced, and damaged conductors should be repaired or replaced. Testing should include voltage measurements, continuity tests, and insulation resistance tests to verify the integrity of the neutral path and identify any potential problems. Repairs should be performed by qualified electricians who are familiar with safe electrical practices and the NEC requirements. In addition to maintenance, proper installation techniques can also help prevent open neutrals. Wiring should be installed according to the NEC requirements, and connections should be made using approved methods and materials. Conductors should be properly supported and protected from physical damage. Equipment should be installed according to the manufacturer's instructions and should be regularly inspected and maintained. Furthermore, surge protection devices can help protect against voltage surges and transients that can stress electrical systems and contribute to open neutrals. Surge suppressors should be installed at the service entrance and at critical equipment locations to mitigate the effects of voltage surges. In conclusion, open neutrals can be prevented through a combination of regular maintenance, proper installation techniques, and surge protection. By taking these steps, you can minimize the risk of open neutrals and ensure the safety and reliability of your electrical system. Now let's delve into the practical aspects of troubleshooting an open neutral using a multimeter. A multimeter is an essential tool for any electrician or electrical technician, and it can be used to diagnose a wide range of electrical problems, including open neutrals. To troubleshoot an open neutral using a multimeter, you will need to perform several tests, including voltage measurements, continuity tests, and resistance measurements. Before beginning any electrical testing, it is essential to ensure your safety. Wear appropriate personal protective equipment (PPE), such as safety glasses and insulated gloves. Energize the circuit whenever possible before performing any tests. If you must work on a live circuit, use extreme caution and follow safe electrical practices. To begin troubleshooting an open neutral, start by checking the voltage at the affected outlet or equipment. Use a multimeter to measure the voltage between the hotline conductor and the neutral conductor, and between the hot conductor and the ground conductor. In a properly functioning circuit, the voltage between the hot and neutral conductors should be approximately 120 volts in a typical residential setting, or 208 or 240 volts in some commercial or industrial settings. The voltage between the hot and ground conductors should also be approximately the same. If the voltage between the hot and neutral conductors is significantly higher or lower than expected, or if the voltage between the hot and ground conductors is different from the voltage between the hot and neutral conductors, it could indicate an open neutral. Next, perform a continuity test to check the integrity of the neutral conductor. Disconnect the power to the circuit and use a multimeter to measure the continuity between the neutral conductor at the affected outlet and the neutral conductor at the service panel. The multimeter should show a low resistance reading, indicating that the neutral conductor is intact. If the multimeter shows a high resistance reading or no continuity, it indicates that there is an open in the neutral conductor. Finally, perform a resistance measurement to check the resistance of the neutral conductor. Disconnect the power to the circuit and use a multimeter to measure the resistance between the neutral conductor at the affected outlet and the neutral conductor at the service panel. The multimeter should show a low resistance reading, typically less than 1 ohm, indicating that the neutral conductor is in good condition. If the multimeter shows a high resistance reading, it indicates that there is a high resistance connection or a break in the neutral conductor. By performing these tests, you can effectively troubleshoot an open neutral and identify the location of the problem. Once you have identified the location of the open neutral, you can take appropriate steps to repair the circuit and restore normal operation. Remember to always follow safe electrical practices and consult with a qualified electrician if you are not comfortable performing electrical work. Also, be aware that identifying an open neutral can sometimes be tricky, especially in complex circuits. It's often useful to systematically check connections and wiring, starting from the point where the problem is suspected and working back towards the service panel. Look for loose connections, corroded wires, or any signs of physical damage. Wiggle test the wires and connections while monitoring the voltage or continuity readings on your multimeter. This can help you identify intermittent opens that may be difficult to detect otherwise. In some cases, an open neutral may not be a complete break in the conductor but rather a high resistance connection. This can be caused by corrosion, loose connections, or damaged wires. A high resistance connection can still cause voltage imbalances and equipment damage, even if it doesn't completely interrupt the circuit. Therefore, it's important to carefully inspect all connections and wiring for any signs of corrosion or damage. Also, be aware that open neutrals can sometimes be caused by problems in the service panel itself. Check the neutral bus bar for loose connections or corrosion. Ensure that the grounding electrode conductor is properly connected to the neutral bus bar and that the grounding electrode system is in good condition. If you suspect a problem in the service panel, it's best to call a qualified electrician to inspect and repair the panel. Working in a service panel can be dangerous, as it contains high voltage circuits that can cause serious injury or death. In addition to troubleshooting open neutrals, it's also important to understand the preventive measures that can be taken to avoid them. Regular maintenance and inspections are key to preventing open neutrals. Check connections for tightness and look for signs of corrosion or damage. Replace any worn or damaged wiring. Use high-quality connectors and wiring that are rated for the environment in which they are installed. Avoid overloading circuits, as this can stress the wiring and connections and increase the risk of open neutrals. Install surge protection devices to protect against voltage surges and transients. By taking these preventive measures, you can minimize the risk of open neutrals and ensure the safety and reliability of your electrical system. Now let's discuss some advanced techniques for diagnosing and mitigating open neutral conditions in more complex electrical systems. In industrial or commercial settings, electrical systems can be quite intricate, with multiple circuits, transformers, and loads. Diagnosing an open neutral in such systems can be challenging, requiring advanced troubleshooting techniques and specialized equipment. One technique that can be helpful is to use a power quality analyzer. A power quality analyzer is a sophisticated instrument that can measure various electrical parameters, including voltage, current, frequency, harmonics, and power factor. It can also capture transient events such as voltage sags, swells, and interruptions. By analyzing the data collected by a power quality analyzer, you can gain valuable insights into the behavior of the electrical system and identify potential problems, including open neutrals. For example, a power quality analyzer can detect voltage imbalances, harmonic distortion, and neutral current, which are all indicators of an open neutral condition. It can also help you pinpoint the location of the open neutral by tracking the voltage and current fluctuations throughout the system. Another technique that can be useful is to use a thermal imaging camera. A thermal imaging camera is a device that detects infrared radiation and converts it into a visible image. It can be used to identify hotspots in electrical equipment, such as loose connections, corroded wiring, and overloaded circuits. Hotspots are often an indication of a high resistance connection, which can be a precursor to an open neutral. By scanning electrical panels, connections, and wiring with a thermal imaging camera, you can quickly identify potential problems and take corrective action before they lead to a complete open neutral. In addition to these diagnostic techniques, there are also several mitigation strategies that can be used to reduce the impact of open neutral conditions. One strategy is to use a neutral current reactor. A neutral current reactor is a device that is installed in the neutral conductor to limit the flow of neutral current. It can help to reduce voltage imbalances and harmonic distortion caused by open neutrals. Another strategy is to use a dedicated neutral conductor for each circuit. This can help to isolate circuits and prevent voltage imbalances from propagating throughout the system. A dedicated neutral conductor also provides a more reliable return path for current, reducing the risk of open neutrals. Furthermore, it's crucial to ensure that the grounding system is properly designed and installed. A well-designed grounding system provides a low impedance path for fault currents, which helps to protect equipment and personnel from electrical shock hazards. The grounding system should be regularly inspected and tested to ensure that it is functioning properly. In some cases, it may be necessary to install a supplemental grounding electrode to improve the effectiveness of the grounding system. In conclusion, diagnosing and mitigating open neutral conditions in complex electrical systems requires advanced techniques and specialized equipment. By using power quality analyzers, thermal imaging cameras, and other diagnostic tools, you can gain valuable insights into the behavior of the electrical system and identify potential problems. By implementing mitigation strategies, such as using neutral current reactors and dedicated neutral conductors, you can reduce the impact of open neutrals and ensure the safety and reliability of your electrical system. Always consult with a qualified electrical engineer or technician when working with complex electrical systems.